I'm Dr. Jeff Groh, and welcome back to Partial Differential Equations. It might seem, after having studied both polar coordinates and then cylindrical coordinates in three-dimensional space, that the next logical step would be to discuss spherical coordinates in 3 dimensions. However, we're going to discuss something that ties together, it's a slight generalization of all of these theories that we've discussed so far. It's called Sturm-Liouville Theory. We're going to define what we mean by a Sturm-Liouville problem. These are differential equations of the following form. Notice we have a second derivative here. Notice that by the product rule, there will be a term that has a y prime on it. There will also be another term that has a y double prime on it. We're going to assume that x takes values in the interval AB, and that we have Robin data In addition, we need to assume something about the regularity of the functions p, q, and r. For regularity conditions, we'll assume that the function p is c1 on the closed interval AB, meaning that the function p must be differentiable and its derivative must be a continuous function. We also need q and r to be continuous functions on the closed interval AB, meaning that they are continuous. We need the function p of x to be strictly greater than 0 on the closed interval AB, so we don't lose that first term ever. The y double prime coefficient will never be equal to 0, and neither will the coefficient of lambda. These are our regularity conditions. A Sturm-Liouville problem is called singular if any one of the regularity conditions does not hold. Or if the interval in question is infinite. So for example, we have Legendre's equation, which takes the form 1 minus x squared y prime prime plus n times n plus 1 y equals 0. So in this case, p is 1 minus x squared. This is going to be singular if the interval contains 1 or negative 1. For another example, there's the parametric form of Bessel's equation, which may be written in the form xy prime prime plus, we're going to write the next term in a special way. It's negative p squared over x plus lambda times x equals 0. Now you can see that both the function q and p can be 0, q is singular, has a discontinuity at 0. So this problem is also singular at x naught equals 0. Here, our interval will be from 0 to a, the typical interval that we've used for expressing solutions to our, say, vibrating drumhead on a disk, etc. As another simple example, consider the differential equation y double prime plus lambda y equals 0. This problem is regular since all the functions are going to be continuous, being constants. Our Robin data is going to be boundary data in this case. We'll assume that the interval is going to be from 0 to pi, and that at both endpoints the value of the function in question will be 0. By trichotomy, we'll have three cases to consider. Case 1 will be lambda equals minus alpha squared, so we get a negative. In that case, a general solution will be C1 cosh of alpha x plus C2 sinh of alpha x, where we have the hyperbolic sine and cosine used in expressing our solutions. Now, to satisfy the boundary data, when we evaluate this at 0, sinh of 0 is 0, cosh of 0 is 1, we get C1 is 0. Evaluating at pi gives us 0 equals C1 cosh of alpha pi plus C2 sinh of alpha pi. We're assuming that alpha is a positive constant without loss of generality. Consequently, alpha pi will be a positive number. Both cosh and sinh are positive in this case. C1 is 0. The only way you can get 0 is if one factor or the other factor is 0, but sinh is not 0 for any alpha pi greater than 0, which means that C2 is also 0. And that gives us that the solution is identically 0 when lambda is a negative constant, negative alpha squared. However, there are still two other cases to consider. The next one will be lambda equals 0, in which case y double prime is 0, in which case y is of the form mx plus b. In order to satisfy the boundary data, we'll have to have a line, a straight line, that passes through the x-axis at two distinct points, and hence both m and b are 0. That means y is identically 0. And we'll move on to the third case. Our eigenvalues lambda in this case can be expressed as lambda equals alpha squared. In this case, we'll have y is c1 cosine of alpha x plus c2 sine of alpha x. We must satisfy the boundary conditions, and so 0 has to be what happens when you get 0 in here. That gives you the first constant is 0. Now for the second boundary condition, 0 equals y of pi. This first term is already 0. We'll have c2 sine of alpha pi. That tells us something about alpha. Assuming that c2 is not 0, alpha must in fact be an integer. This gives us a class of what we call eigenfunctions, corresponding to our eigenvalues, lambda equals n squared. One thing to note about this regular, non-singular Sturm-Liouville problem is that to each eigenspace there is one eigenfunction essentially spanning the entire eigenspace, which means that the eigenspaces are one-dimensional for each different eigenfunction. We have the important theorem. In a regular Sturm-Liouville problem, all eigenvalues are real. So first of all of the eigenvalues will be real numbers. Also, the eigenvalues will be discrete in the sense that there are no points of accumulation for these eigenvalues on the real line. The limit as n goes to infinity of these will be infinity, so they'll have to be spread out. The eigenspaces are one-dimensional, so there will be a single function that represents all of the eigenfunctions in a particular eigenspace. And also, the eigenvectors from different eigenspaces are orthogonal. Assuming that we're using an inner product with a weight equal to r of x. So if we take the inner product of f and g, we'll have this weight r of x. Note how the original Sturm-Liouville problem is telling us exactly what weight to use on our inner product, and that's very convenient. In our proof, let's suppose that j is not k. We're going to have lambda j, lambda k, and then yj and yk being eigenfunctions associated with these different eigenvectors. These have to satisfy the same Robin data. With Robin data, we're assuming that not both C1 and C2 can be 0. Assuming that we're solving this system of linear equations for C1 and C2, this implies then, since we have two distinct solutions giving us 0, that the coefficient matrix must in fact be singular. Note that this is not really a Wronskian. Since yj and yk come from different differential equations for different lambda j and lambda k. So this is not really a Wronskian. But similarly, we also have this other wb. Here we'll have yj of b, yj prime of b, yk of b, yk prime of b, and this must also equal 0 at the other endpoint. Since p of a and p of b are finite, and I guess on infinite intervals we'll take a limit, we have p of a, w of a, minus p of b, wb, must in fact be 0. If L is one of j or k, and yj, yk correspond to lambda j and lambda k, then we have the following. Plugging these into the Sturm-Liouville problem, we have to get a true statement. And hence this must be true for both L being j or k. We'll multiply the expression with L equals j by y sub k throughout the entire equation. When we do, this last term will have y sub j, y sub k on it. This lambda term will have a lambda j, and so this term, I want you to keep that in mind, has a lambda j. On the other equation with L equals k, we'll multiply through by y sub j throughout the entire equation. We'll have a y sub k, y sub j multiplied on at the end. But this will be lambda j this time, which means that when we subtract, the q terms will cancel out exactly, and we'll have the following: y sub k times p of x y sub j prime quantity prime minus y sub j times the other second order term y sub k prime prime. The lambda terms are going to be different, and we'll be subtracting them. First the lambda j minus the lambda k. If we move those to the other side, we'll have negative lambda j minus lambda k all times r of x, yj, yk multiplied together. Now, since lambda j and lambda k are assumed to be different, if we integrate both sides, the right-hand side will have a non-zero factor times the weighted inner product of yj and yk. Remember, two functions are orthogonal if their inner product is equal to 0. So the goal will be to show that the other side is in fact 0. So you can see how the right-hand side is going to turn out. The question is, how does the left-hand side turn out? Well, we're going to have to work with this a bit first. So let's apply the product rule. When we apply the product rule, we'll have yk p prime of x yj prime plus yk p of x yj double prime, and then minus what we have over here, yj p prime of x yk prime, still subtracting yj p of x yk double prime. Now, let's compare this to the derivative of p of x w, which is the derivative of p of x times y1 yj yk prime minus yk yj prime. And you'll see that you'll have this p prime of x times this w, which we have up here, plus p of x times this w prime, and w prime, using the product rule, has a yj prime yk prime plus yj yk prime prime minus yk prime yj prime, which cancels out, and then minus yk yj prime prime, and that's what we are seeing here. So we get exact equality with what we have for the derivative of p of x times w. This exact equality certainly makes the integral easier to figure out. When we integrate the derivative by the fundamental theorem of calculus, the antiderivative will be p of b wb minus p of a wa, and that's minus lambda j minus lambda k, the integral from a to b of yj of x yk of x r of x dx, or minus lambda j minus lambda k, the inner product of yj and yk. Since the left-hand side has already been shown to be identically zero, and since yj and yk are not equal, since we're dealing with different eigenspaces, that implies then that yj is in fact orthogonal to yk, since the inner product is zero. That leaves only one issue left to prove, and that is that each eigenspace itself is one-dimensional. So in this case, we'll assume that y1 and y2 correspond to the same eigenvalue lambda, in which case we look at the Robin data again. And since C1 and C2 are not both zero, in order to have non-trivial solutions here, we have to have this W equal to zero. In this case, since the differential equations are the same, since they correspond to the same lambda, this is an actual Wronskian, which implies then that y1 and y2 are linearly dependent by the old theory from elementary differential equations. This implies then that the eigenspace corresponding to a particular eigenvalue is 1D. And that's the end of the proof. Instead of Robin data, we sometimes impose periodic data. So y at a will be the same as y at b. Y prime at a is the same at y prime of b. And this is not really Robin data anymore. And in the last theorem is false in this case. And we'll give a simple example. Here, y of negative pi equals y of pi. So this function is 2 pi periodic. Y prime at negative pi equals y prime at pi. So the function value and its slope are equal to each other at the endpoints between negative pi and pi. Clearly, a general solution is going to be c1 cosine of nx plus c2 sine of nx. Evaluating at negative pi, the second term will go away. You'll have cosine of n times negative pi. The negative will go away because cosine is even, and so you get the same value when you substitute x equals pi, which of course this term still goes away. And when you plug in pi here, you get the same thing as cosine it with a negative n pi as well. When you take the derivative, you'll get a negative sign here and a cosine here. These terms will cancel, and these terms will be even, and hence you'll get the same value at negative pi as you do at pi. And so we have a 2D solution space. The span of these two linearly independent functions will give you the solution space for lambda equals n squared. As another quick example, we'll have y double prime plus lambda y equals 0, which is a fairly general Sturm-Liouville problem. We'll have Robin data. The first condition will be y prime of 0 equals 0. The second condition will be y of 1 plus y prime of 1 equals 0. There are 3 cases to consider. We'll start with lambda being 0, since that's fairly simple. If lambda is 0, then y double prime is 0, and that gives you y is mx plus b, a straight line. If y prime at 0 is 0, y prime would be m. That means m is 0. So y is a constant. If y is a constant, then y prime at 1 must be 0, but still y of 1, which is b, will also have to be 0. And that means y is identically 0. Not a very interesting case. If lambda is less than 0, we'll set lambda to be minus mu squared. That gives us a general solution of the form c1 cosh of mu x plus c2 sinh of mu x. Notice that if we take the derivative and evaluate at 0, the derivative of cosh is sinh, and the derivative of sinh is cosh. So sinh at 0 is going to be 0. You'll have 0 equals mu c2 cosh at 0, which is 1. Mu is not 0, and that implies that c2 is 0. So these terms all go away. That makes it easier to evaluate the second Robin condition. 0 will be equal to y at 1. That's going to be c1 cosh of mu plus y prime at 1. That's going to be c1 mu sinh of mu. This equation implies that either c1 is 0, and that would imply y is identically 0, or we'll have the tanh of mu will move say this term, we'll cancel the c1's off, move this term to the left, and then divide, and then we'll have to divide the mu off. We'll have tangent of mu equal to minus mu. Now, the tangent function goes something like this. And if you have a positive mu, which we're assuming we have, the only way that tangent is going to be, well, tangent is never negative whenever mu is positive, which means that you only get a solution to this equation when mu is 0, and that's a contradiction. And so we don't get any solution worth mentioning in this case at all. By trichotomy, we're down to one case left. We'll set lambda equal to positive mu squared. And then our differential equation will be y double prime plus mu squared y equals 0. That has a general solution of the form c1 cosine of mu x plus c2 sine of mu x. Again, evaluating at the first Robin condition, the derivative will have a negative mu sine of mu x. Evaluated at 0 gives you 0. We'll have c2 mu cosine of 0, which is 1. And we then deduce, since mu is not 0, that c2 is 0. So we lose these second terms altogether. That leaves only the second Robin condition to verify. And we'll have 0 equals y at 1. That's going to be c1 cosine of mu. And then the derivative minus c1 mu sine of mu, all equal to 0. We can factor the c1 out. We'll deduce that c1 is not 0, because then we'll just have no interesting solutions at all. So if c1 is not 0, this other condition will have to hold. This last condition amounts to the tangent of mu equals 1 over mu. Well, where do these functions intersect? Perhaps a better way of looking at this is cotangent of mu equals mu. The cotangent function looks like this, and the function y equals mu comes off at a 45-degree angle, and we'll have points of intersection, mu1, mu2, mu3, trailing off to infinity. This gives us a class of solutions y sub n equals the cosine of mu sub n x. These are one-dimensional subspaces. The eigenvalues are lambda equals mu n squared, lambda n equals mu n squared. As part B to this last problem, I want to express the function x times 1 minus x as an eigenfunction expansion. To do this, we'll suppose that f of x, which is x times 1 minus x, which can be expressed as the sum as n goes from 1 to infinity, of these cosine, an cosine of mu n x's. All you need to do is to figure out the coefficients a sub n, and to do that, you take inner products with respect to these eigenfunctions, cosine of mu n x. By our Fourier series theory, these should be equal to the inner product of f of x with our cosine mu n x using the appropriate weight over cosine mu n x, comma, cosine mu n x from our standard Fourier series theory. In this case, we can assume that the weight function would be mu n squared. As a constant, it would come out of both of these integrals and cancel out. So we can just use a weight of 1 in this case. Let's look at the inner product of the cosines. This denominator here will be integrating from 0 to 1. Cosine of mu n x squared. We will, of course, use the half angle identity. 2 mu n x. Integrating, we'll have x integral of cosine sine, but we have a 1 over 2 mu n. We're evaluating from 0 to 1. Plugging in 1, we'll have 1/2 times 1 plus 1 over 2 mu n sine of 2 mu n. And when you plug in 0, both terms go away. So this is just it. These will be our denominators. We still have to integrate f times these cn's. I'll leave it to you to figure out that you get twice the sine of mu n's minus mu n minus mu n cosine mu n divided by mu n cubed. We have then that the function x times 1 minus x may be represented as we'll have these coefficients divided by these coefficients. That gives us a 2 over 1 plus 1 over 2 mu n sine of 2 mu n. We'll use a double angle identity there. All of that times the cosine of mu n x. We can only simplify this a little bit. Like I say, this is 2 sine mu n cosine mu n. This 2 will cancel this. We can break one of these off and put a mu n and cancel this mu n. That gives us the sum, as n goes from 1 to infinity, of 2 sine mu n minus mu n cosine mu n times a 2 divided by mu n squared times 1 mu n plus sine mu n cosine mu n, all times cosine of mu n x. So these are your coefficients. A classic example would be the hanging chain, which we're allowing to move. This was discovered in 1732 by Daniel Bernoulli. And the differential equation in question is going to be UTT equals the gravitational constant g times x uxx plus ux. Here, x will take values between 0 and L, and t will take values greater than or equal to 0. The data will be u at L, t, is 0. It's going to be fixed here. What is the velocity at time 0? That will be any velocity profile that you wish. Also, what is the initial displacement? That will be any displacement function that you wish, other than the fact that at x equals L, the displacement must be 0. We will, of course, assume a separability condition, in which case we'll have x t dot dot equals g times x prime prime t plus x prime t. We divide everything in sight by xt. We'll have t dot dot over t equals g times x prime prime over x plus x prime over x. This must be equal to some constant k. We'll divide this g off first. We'll put it over here, but you'll see then that this has to be negative. This will have to be some negative lambda squared. That will give us some periodic thing going on with respect to the function t. We'll have the cosine of square root g lambda, all times t here. The second equation we multiply through by big X. We'll move this term over and note that this is a product rule. It's x prime prime plus a lambda squared x equals 0, and this next equation looks very reminiscent of a Bessel's equation of order 0, of parametric form, but it isn't quite. You can see that if you were to take the product rule here, you'll have an x prime. You'll also have an x times an x prime prime term. To get a x squared in this location, which you need for the parametric form of Bessel's equation, you'd have to multiply by x squared, but that would give you an x cubed times the x prime prime. And so something is amiss. It's not quite Bessel's of order 0. But we can make it into a Bessel's equation of order 0 by making a substitution. The substitution is s equals 2 root x. What does that do to our derivatives? We'll have ds dx times d ds using the product rule. But ds dx is 2 over 2 root x dds, but keep in mind 2 root x is s, so you'll have 2 over s dds. So all of your derivatives with respect to x become 2 over s times the derivative with respect to s. What does that give you? Here, s divided by 2 is going to be root x, so squared will be x. We'll have s squared over 4. We'll have then 2 over s times the derivative with respect to s of x, all times 2 over s times the derivative with respect to s. Now, where does everything fall out now? These 2's are going to go away. When we do the product rule now, we'll still have this 1 over s out front. We'll have 1 times x prime, the primes now will be derivatives with respect to s, plus s times x prime prime plus lambda squared x equals 0. You can see now we'll have a 1 over s, and this will cancel out. Multiplying through by s squared, we'll have an s here, we'll have an s squared here, an s squared in this location, and just an s in this location. Let me rewrite that. We'll have then s squared x prime prime, where primes are derivatives with respect to s, plus s x prime plus lambda squared s squared x equals 0. Exactly a Bessel's function of order 0. We have to be cognizant of our boundary conditions. Remember, our substitution is this, so S max is going to be 2 root L. So if x is equal to L, S is going to be 2 root L, and we need to know what happens x at 2 root L. That should give us a value then of 0, because the thing is not displaced at the top of the pole. So when we plug 2 root L in, we get a root. That means then that all of our eigenvalues are going to be form alpha 0k divided by 2 root L, so that when we plug in to our Bessel's functions, alpha 0k over 2 root L times x times s, whenever s is equal to 2 root L, we'll get a root, and that will give us a solution. But substituting back for s equals 2 root x, we'll have basically a root x over L multiplied by these roots, alpha 0k. That gives us then a general solution of the form the sum n goes from 1 to infinity. We'll have these Bessel's functions. I'll write these as alpha sub k's just for sake of argument. It's going to be root x over L. We'll have a sub k cosine root g over L alpha k t plus these b sub k's times sine root g over L alpha k t. We now just have to get the initial data right. If we set t equal to 0, this term will go away. This will be 1. We'll have the ability to solve for these a sub k's. The initial data then will be the sum, as n goes from 1 to infinity, of the j0 alpha n, I guess these should be n's, times root x over L times a sub n, and I guess all of these should have been n's to begin with. We can then just take inner products to figure out these coefficients a sub n. We'll have a sub n equals 1 over L j1 squared of your alpha n's, integral from 0 to L u naught of x times the Bessel's function of order 0, alpha n root x over L dx. For the velocity data, we'll have u naught, the derivative, ut 0 here, and everything else is more or less the same except for the fact that it'll apply to the derivative. The minus sign here evaluated at 0 will be 0. You'll have cosine here. You'll end up with the bn's. And I'll just tell you that these can be simplified as 2 over alpha n j1 squared of alpha n times, you'll have 1 over the root of gl, integral from 0 to L, ut 0 of x, j0, alpha n root x over L dx.